Continuing on in the aqueous ionic equilibrium chapter, we come to titrations and pH curves. Now, this section is going to be long. This video is going to be, well, I'm going to chop it up into a number of shorter videos. Yeah, this is pages and pages and pages of material. The good news is it's very repetitive. So the first couple of calculation examples, we'll go through it kind of slowly, but as we go on, I'll just go really quick through it. It's a video. You can pause it at any time to read the notes, even though they tend to be blurry on the sides and whatnot. Okay, hopefully you've done titrations before. Our first titration we're going to look at is a strong acid, and we're going to titrate it with a strong base. So here's our burette, and in the burette we have 0.1 molar sodium hydroxide. I just chose a strong base. I chose 0.1 molar just because I like that molarity. It's a fun molarity to do reactions with. Not too concentrated, not too dilute, and 1 is a nice number for calculations. Now, in this Erlenmeyer flask down here, we're going to have 25 milliliters of 0.1 molar HCl. So here's our strong base in the burette. We're going to be slowly adding that into this acid that's in the Erlenmeyer flask. The reaction HCl aqueous plus NaOH aqueous is going to go 100% to NaCl plus H2O. Now, first definition here is the equivalence point. The equivalence point is just standard stoichiometry. Here we have a 1-to-1 ratio here. When the moles of base that you have added into the burette equals the moles of acid you started with. Now, in these calculations we're doing now, we know a lot of information. We know the molarity of the base. We know the molarity and the volume of the acid. And so we can do a quick calculation. Since at the equivalence point, moles of base equals moles of acid, we can calculate our moles of acid, the molarity, 0.1 molar times 0.025 liters, or 25 milliliters, gets 0.0025 moles of HCl. So that tells us that at the equivalence point, we're going to need 0.0025 moles of NaOH because of our 1-to-1 stoichiometry here. So if we have 0.0025 moles HCl, we have to add 0.0025 moles of NaOH to reach the equivalence point, to totally neutralize all of that acid with the base we're adding. We can calculate at this point, well, how many milliliters of NaOH is that? Since we have its concentration, we know 0.1 moles per liter times the liters is going to be 0.0025 moles. X equals 0.025 liters because just solve for X in this equation, and that's 25 milliliters. Now that should not have been shocking. If we have the same concentration of acid as we have base, 0.1 molar, and this is 25 milliliters, we're going to need 25 milliliters of base to add. Note when you're in the lab lots of times, when you're actually running the experiment, you often do not know the concentration of the acid down here. But here we know everything, so we can go through a bunch of calculations. Something to note. It gets to be quite the pain converting to liters all the time. You know, because when we had to convert this to liters up here, we had to go 0.025 liters, and that gave us this tiny amount of moles, 0.0025 moles and everything like that. That's a pain. It's a pain for your calculator. It's a pain for your brain. So we have an easier way. We have a unit called the millimoles, and that shouldn't be anything new. If we have liters and milliliters, we know 1 milliliter is 0.001 liters, then 1 millimole is 0.001 mole. Milli just means 1/1000th. So 1/1000th of a mole is a millimole. And that is given the abbreviation mmol, millimole. The nice thing about this and how it's going to work is because 1 mole per liter, or 1 molar, is the same as 1 millimole per milliliter. So when we went up here, a 0.1 molar HCl solution is 0.1 mole per liter or 0.1 millimoles per milliliters. And so when you use millimoles per milliliter, our numbers that we're using just come out nicer. Because with this titration of the acid, up here we're using moles and liters and everything here, if we convert to millimoles per milliliter, we know that 0.1 millimole per liter, 0.1 millimole per milliliter times 25 milliliters is 2.5 millimoles. And so the volume of base we're going to need to add, we do the same calculation that we did right here, and we come up with 25 milliliters. And I like doing math with 2.5 and 25 much more than I like doing math with 0.025 and 0.0025. So from now on, we're going to use millimoles and milliliters when we do our titration. It's just easier. All right, so let's do some calculations for this situation that we have set up for this burette and this Erlenmeyer flask. So the first thing we need to calculate is what's going to be the pH of this solution. What's the pH before any sodium hydroxide is added? So at this point, we just have the 0.1 molar HCl. That's all that's in the solution. All right. Well, that's a pretty easy pH calculation. If you have 0.1 molar HCl, that's a strong acid. We know the concentration of H plus is also 0.1 molar because it's associated 100%. Therefore, the pH is negative log of 0.1, pH equals 1. So that in this flask down here, before we had added any base, the pH is 1 of this HCl. And when we're looking at the pH, we're always going to be looking at the pH down in this flask. All right, so our next question, what's the pH after 5 milliliters of sodium hydroxide is added? Well, the question is, what's the sodium hydroxide going to do? If we've got sodium hydroxide here, HCl here, well, we know it's going to undergo this reaction. The HCl plus NaOH goes to NaCl plus H2O. Now, before, you'd done this in Gen Chem 1 where you just, okay, no problems here, limiting reagent type of problem. But since now we're really fond of and good at ice tables, let's introduce another type of table here. We've seen it before. Our ICF table, or our ice-like table, as they say, because this is just a stoichiometry problem, and I think you're going to find stoichiometry problems are a little bit easier to figure out what's going on when you use these tables. Of course, remember this ICF, it's the final thing. This is a 100% reaction, so our units need to be in moles, not molarity for these tables, moles. But we recall from our calculations, we had 0.25 moles of HCl. If I added 5 milliliters, I know 5 milliliters times 0.1 millimole per milliliter, because that's our concentration of NaOH, 0.1 mole per liter or millimole per milliliter, tells me I've got 0.05 millimoles of NaOH added. And so now it's just a limiting reagent problem. Okay, I've got 2.5 moles of HCl, 0.5 moles NaOH, it's a 1-to-1. So I know that NaOH is my limiting reagent, so I'm going to subtract off the 0.05 moles for limiting reagent, subtract off the 0.05 moles from this HCl, and I have 2 moles of HCl left. Note our products we're not worrying about because we're after pH, and NaCl, sodium chloride, is an ionic compound, conjugate base of a strong acid, conjugate acid of strong base. NaCl does not affect pH. Water does not affect the pH. So this is going to be a neutral solution on the product side, so the only amount of acid or base will come from the leftover reactant. We have 2 millimoles of leftover HCl, so that's the only thing that will determine the pH. So, well, the problem is if we want the pH, we know pH is a negative log of the concentration of H+. This is HCl, it'll associate 100%. But this is moles, or millimoles. This is millimoles of HCl. I need to convert those millimoles into molarity. Well, I know my concentration of HCl is millimoles per milliliter. I have 2 millimoles. But note, I started with 25 milliliters of HCl. I added 5 milliliters of base, so my new total volume is 30 milliliters. 25 milliliters to start with plus 5 milliliters makes 30 milliliters as my new volume. So 2 millimoles left over divided by 30 milliliters, my original 25 plus the 5 NaOH that I added, gives me a concentration of HCl of 0.066 molar. pH is a negative log. Well, that's 0.066 molars concentration of HCl. Since it's a strong acid, dissociates 100%. That means that's concentration of H+. pH is a negative log of 0.066, my concentration of H+. pH equals 1.17. So after adding 5 milliliters of strong base, the pH went from 1 to 1.17. Okay. Let's now add 10 milliliters of NaOH and see what happens. Well, after 10 milliliters of NaOH added, same, we have an initial change final table. We note the nice thing about this, since we started with 25 milliliters of 0.1 molar HCl here, our initial moles of HCl will always be 0.25. You can just put that 0.25 in there. That will always be our initial moles of HCl. All right, well, for our 10 milliliters of NaOH, right here, we got a 0.25. Note it's 10 milliliters of NaOH, so that'll equal 1.0 millimoles. Here's the calculation up here. NaOH is still the limiting reagent, 1 millimole compared to 2.5, so subtract 1 millimole from both these. We've got 1.5 millimoles of HCl left over. And just like we did before, the pH is a negative log of that 1.5 millimoles divided by 35 milliliters. Our 25 milliliters of acid we started with plus our 10 milliliters NaOH gives our total volume of 35. pH is 1.37. Let's do the calculation again, but after 20 milliliters of NaOH. Okay, our initial amount of HCl is 2.5 millimoles. 20 milliliters is 2.0 millimoles of NaOH. It is still a limiting reagent. We have 0.5 millimoles of HCl left over. Our 0.5 millimoles divided by our new volume, 45 milliliters. Take the negative log of that to get the pH of 1.95. Recall that we're at the equivalence point, we're going to have 25 milliliters of NaOH added. So we're all the way up to 20 milliliters of NaOH added, going up to 25. But interesting things happen as we get close to 25. So we're not going to jump to 25 next. We're going to do some more calculations because we're going to end up plotting this data on a chart, and we want to get a good idea of what this curve is going to look like. All right, so part 5, the pH after 24 milliliters of NaOH added. No, 1 milliliter off of the 25 we're going to eventually add to get the equivalence point. Well, same calculation. We start with 2.5 millimoles of HCl. Now we're at 2.4 millimoles of NaOH. It's still the limiting reagent. We've got 0.1 millimoles of HCl left over. Our 0.1 millimoles divided by our 49 total milliliter volume. Negative log of that. pH is 2.69. Oof. Look at this next calculation. We're at 24.5 milliliters of NaOH added. Same business. Initial 2.5 millimoles of HCl, 2.45 millimoles of NaOH. We'll have 0.05 millimoles of HCl left over. 0.05 millimoles divided by 49.5 milliliters is our concentration of H+. Negative log, our pH is 3. And I'm not done yet before I get to 50 added. I'm doing 24.9 milliliters of NaOH added. Realize 24.9 milliliters. We're within one drop or two. We're within a drop or two of reaching the equivalence point. We've added almost 50 milliliters. Now we're within one drop or so, maybe at most 2 drops of 50 milliliters added here. And let's look at the pH. Same thing. Now we got 2.49 millimoles of NaOH. We got 0.01 millimoles of HCl left over. pH is negative log 0.1 over our volume. Our pH is 3.70. So note, we started at a pH of 1. Before we added any base, the pH was 1. We've now added 24.9 milliliters of base, and our pH is 3.7. Finally, we're going to add this last drop. What happens when we add that last drop of NaOH? Well, now our millimoles of NaOH is 2.5. Note we have no HCl and no NaOH left over. We're at the equivalence point. The moles of acid equals moles of base. They totally have neutralized each other. But note, NaCl and H2O don't affect pH. This is just salt water. Well, what's the pH of water? Neutral water with a little salt in it? It's 7. pH is 7. It's the pH of water because our only source of H plus and OH minus is from Kw at this point. The concentration of H plus times the concentration of OH minus. And we know that at this point, if it's just water, that the Kw is 1 times 10 minus 14th. Concentration of H plus is going to equal 1.0 times 10 to the minus 7 square root of Kw, and our pH then is 7. So note, we added 24.9 milliliters of sodium hydroxide, got the pH to go from 1 to 3.7. It went up by 2.7 pH units. Add one more drop, shoots up to a pH of 7. Goes up another 3.3 pH units with one drop. Okay. Let's add one more drop, go to 25.1 milliliters of NaOH. Note, at this point, we have HCl, NaOH. Start with our 2.5 millimoles of HCl. Now we've got 2.51 millimoles of NaOH. Note, it's no longer the limiting reagent. We have extra NaOH. HCl is now the limiting reagent, so we get rid of all the HCl. Subtract the amount of limiting reagent from our excess reagent. We'll have 0.01 millimoles of NaOH left over. Note, since we're looking at NaOH, the pOH is negative log of the 0.01 millimoles of OH divided by 50.1 milliliter total volume. pOH is 3.7, pH is 10.3. Look at that change. We're harping on it again. We were at a pH of 3.7, added one drop and went up to 7, added one more drop and went up to pH of 10. This is just one drop, two drop change. That gave us a pH from 3.7 to 10.3. When you are around the equivalence point, when you have fairly equal amounts of acid and base, the pH is just extremely variable. Just a little bit more base and the pH shoots up. Just a little bit more acid, the pH shoots down. This is why you need buffers. Recall buffers from our previous discussion. You need buffer solutions because what's the pH of blood? Well, pH of blood is a little above 7, which means the tiniest bit of acid is going to take your pH of blood way below 7 and you will die. The tiniest bit of base will take your pH above 7 and you will die. So your blood is very well buffered right at 7. You need those buffers to not get these very wild pH changes that would kill you if you drank some orange juice. Oh my goodness, it has a pH of 2. What would happen to you? Well, your blood's buffered, so you don't worry about that. All right. Okay. Let's keep on going. Let's add 10 extra milliliters. Let's add our 5 extra milliliters. Let's add 30 milliliters of NaOH added. And it's the same calculation. Our initial HCl is 2.5. Now we've got 3.0 millimoles of NaOH. HCl is a limiting reagent, so I got 0.5 millimoles of NaOH left over. The pOH is negative log of 0.5 over 55. Our number of millimoles divided by our new volume. pOH is 2.04. Remember, pH equals pOH plus pH equals 14, so pH is 11.96. Last one more. pH after 40 milliliters of NaOH added. Go through the calculation again. pH is 12.36. And now we're going to plot that data. And I just put the dots on here. I messed up. We didn't do a 15 calculation, so that dot doesn't belong there. But if you plot the data, this is what you get. The curve starts out very low, rising up just a little bit, and then right when you get to right around the equivalence point, boom, it shoots up really high and then starts leveling out again. So this curve here is your plot of the pH versus milliliters of NaOH added. And this is what you see with a strong base being added to an Erlenmeyer that has strong acid a little bit at a time. Titration is adding a little bit of a reagent at a time. So this is a strong acid, strong base titration curve. That is what it looks like. And this is why titrations do such a good job of figuring out how much acid would be in that Erlenmeyer flask, because once you get around the equivalent point, you get tremendous changes in this pH right here. Ooh, well, this video ran 20 minutes, and we just did this one problem. We've got more titrations to do.